everybody. Thank you so much for joining us for another episode of Echo Live. Thank you for your patience. I know we're a few minutes behind today. We were having a little bit of difficulty with our live stream, but we'll wait just a few moments for people who might still be trying to join us on any of our live platforms. Thank you to those who are waiting patiently inside our Zoom platform. If you haven't done so already, please feel free to introduce yourself in the chat feature. If you're joining us on Facebook or YouTube, send us a comment. You can introduce yourself, tell us where you're watching from. You could tell us what grade you're in, or even what's been your favorite episode of Echo Live so far. I'd love to know what you at home think. Now, today on Echo Live, we'll be talking about optical illusions, which is kind of some interesting science. So I've got a couple demonstrations and optical illusions to share. And then we'll talk about the science, or the neuroscience really, behind what's happening when we look at an optical illusion. The very first one I have to show you is actually right up behind me on my screen. Now, this is actually a static image. I'm going to scoot over to the side in just a moment here, and I want you to tell me, does this image appear to be moving at all to you? Tell me, what do you think? You might need to stare at it, maybe let your eyes relax just a little bit. We talked yesterday on Echo Live about the mammalian eye. So we did a sheep eye dissection yesterday, and we talked about how our eyes receive information from our environment. So go ahead and tell me in the chat, does this video, or does this, it's not a video, does this image appear to be moving? I'm seeing some friends on all of our platforms starting to chime in and tell me that it does appear to be moving. Now, this is a static image. This is just a JPEG that I pulled offline in order to show you. This one is specifically called the Moray effect. So optical illusions are often named after the person who designed them. And we'll talk about the design of optical illusions as we move through our program today. So let's first talk about how exactly our brain processes visual information. So we know exactly how light enters our eyes. We talked yesterday about how the light that we see, or visible light, needs to travel through our eyes, through a few different tissues and structures that we talked about. And then it gets to our retina, which then sends information down our optic nerve to the brain. So we have some images here of the pathways in the brain where these images are processed. So the raw information travels through the optic nerve and arrives in the brain in the occipital lobe, which is at the back of your head, kind of near the base of your skull. So that is the occipital lobe where the information is received. But in order for this information to be processed, for us to understand what we are seeing, there are two major pathways involved in this. So information splits off. The first thing our brain needs to know when we're looking at something is, what exactly are we looking at? We call this object processing. And the pathway that our brain uses to process what we're looking at is called the ventral stream. So the ventral stream is noted with these red arrows. They travel down through your temporal lobe, which is located just behind your ears, or kind of inside your ears, then up to the frontal lobe, which sits just above your eyes. But again, these are all parts of the brain. The what pathway, or the ventral stream, tells us things like, what color is the thing we're looking at? How about texture or details, the shape, or even the size of this object or thing that we're looking at and receiving those visual cues from? But we also need to understand how this object is located, or where we might find it. We call this spatial processing. So spatial processing happens through the dorsal stream, which is noted in these blue arrows. So this information travels from the occipital lobe up and through the parietal lobe. Up at the very tip top of your head is your parietal lobe. The spatial processing stream tells us whether something is moving. It tells us where exactly it's located. Spatial transformations, which means, is it changing at all? So is the object staying the same size or shape, or is it moving around inside a space? And also spatial relations. So how far away is this object from yourself or from other objects that you might be looking at? Now, the brain is extremely smart and extremely complicated, And there are thousands of pathways in your brain working at any given moment. When we talk about optical illusions, some people like to say that optical illusions are something tricking your brain or your brain misfiring or receiving incorrect information. And that's not necessarily the case. When we're seeing something that's an optical illusion, it really is just a result of these two pathways trying to fill in information that your brain might not have directly. Because the brain is a powerful tool, and we actually don't have to tell the brain everything we're looking at. Even if something is missing from an image, your brain will start to fill it in with prior knowledge or things that it thinks should be there. Now let's start with a pretty simple optical illusion here. I have two paper arches, and I want you to tell me in the chat or in the comments which one is larger. So I'm holding them just one on top of the other. We have a purple arch and a blue arch. And I just want you to tell me in the chat which one is larger, which is the larger arch. So take a moment to think about it. Again, we have purple on top and blue on the bottom. So go ahead, tell me in the chat which one is larger, which one is the bigger of the two. Zoe tells me the purple one. Jennifer and Christina both think the blue. Becky thinks maybe there's no difference between these two arches. So take a guess, take a moment to really think about these arches. They're being held right next to each other, right on top of each other. And you're just trying to figure out which one is larger, which can be tricky, right? Because you're not up close here in the studio like I am. And we see some really great guesses. We've got guesses for purple, blue, and some people saying neither, and some people saying both. These are great answers. Now, we talked about that your brain is always taking information and turning it into cues. So this might have something to do with spatial awareness. Now, if I take my two arches and I lay them right on top of each other, if you said that they are the same size, you are absolutely correct. So no matter which one I put in front, you can see that these two arches are actually the exact same size. I actually cut one out and then traced it and placed it right on top of the other one and cut the other arch. So I know that they are exactly the same. But when we had them arranged in such a way, right, depending on which order I put them in, our brain might tell us that the one on the bottom is the larger of the two arches. And that really just has to do with how they meet. So if I hold them up together and we look where the two arches meet, right, since they have this angular cut in, and since where they meet, we see that the blue one seems to have a larger circumference or a larger arch on top, right? We think that this one might be the larger one. That's your brain taking spatial cues. Your brain is always comparing objects with other things around it. So if you thought the bottom one was larger, that's okay. That is your brain trying to process information just using the cues around you. You weren't able to hold them one on top of the other like I am. You couldn't manipulate them in any way. You also can't necessarily use a ruler to measure something on the computer screen, right? But your brain is a powerful tool that almost works like a calculator or a computer, and it's always trying to figure things out like a puzzle. So that's just one example of an optical illusion, just because of how our brain processes the information it receives. Now we're going to talk next about some famous optical illusions, some of my favorite ones that I've seen online or in books or even on the back of cereal boxes. I've found have actually been the best place to find optical illusions. That's actually where I found this one. I think way back in about 3rd or 4th grade, I had a box of cereal that had a bunch of optical illusions on it. And it really got me interested in thinking, well, why are these illusions tricking our brains? But there are some pretty famous ones that have popped up online over the last few years as well. One of them being the spinning dancer. So the spinning dancer was actually designed by a graphic designer called Nobuyuki Kayahara. So if we get our dancer spinning here, the optical illusion involved in this image has some people imagining that the dancer is spinning clockwise. So think about clockwise. And other people view the dancer as spinning counterclockwise in the opposite direction. So take a moment to look at our spinning dancer here and tell me, is the dancer spinning clockwise? So is her foot traveling across the front in that direction? Or is she spinning counterclockwise, and her foot is moving across the screen in this, oops, let me get my mouse here, in this direction. All right, take a moment, tell me clockwise or counterclockwise, do you see the dancer spinning? Our brains will really choose one direction at first. I think most people, based on statistics, when they had people analyze this image, most people actually view the dancer as spinning clockwise. So from her foot traveling in that direction across the front. Less, but not much less people view the dancer as spinning counterclockwise. But if you really focus on the image, you can actually get the dancer to switch directions. The reason that people have trouble distinguishing which direction that the dancer is spinning is because it's pretty ambiguous. There's not a lot of information told to our brain from this image since it's just a silhouette and we don't see any of her body features. To outline this, if you're having trouble thinking about how others might view this dancer as spinning in the opposite direction, someone drew some outlines on this photo for us, which is actually very, very helpful. So both of these images on the right and left are copied and pasted from the center image. So the dancer is in the same position in each of these three images. What our brain does is it fills in the information that we don't necessarily get from the black image. So in this one, we can see that this is an example of the dancer spinning counterclockwise. In this one, we're looking at the inside of the blue leg and the outside of the red leg. In the opposite photo, we said that this is the same image, but the red leg, now we're looking at the outside on the left and the inside of the blue leg on the right. So it really is tricky. Now let's try to switch the dancer spinning in our minds. And we can do that. There's a simple way to do it. It takes a little bit of practice, but we'll try it. The easiest way to try to get the dancer to spin or change directions in your mind is by focusing on one part of the dancer's body. So try focusing either on the head or on the foot and see if you can get the dancer to spin in the opposite direction as you originally thought she was spinning. This took me a bit of practice. We'll give you about 30 seconds to try to get the dancer to switch ways here, but we'll definitely post a link to this video or this GIF that you can stare at if you want to practice this after Echo Live is over. If anyone has gotten the dancer to switch directions to start spinning the opposite way, tell me in the chat. Did you get her to switch or are you still having some trouble? Like I said, this took me a little while, but this trick really helped me by focusing either on the dancer's head or on her bottom foot that she's standing on. All right, well, while we wait about 10 more seconds, if you haven't gotten the dancer to switch already, let's start talking about another image. So 3, 2, 1, make sure you tell me if you got the dancer to switch or you did not. But our brain, right, can receive all sorts of cues. This is also a pretty famous type of illusion that we call two faces. So this one we call two faces because depending on what your brain processes first, which image or which part of the image your brain focuses in on, we can either see a face facing right towards the camera, so staring straight at us. You might notice this if you were to first choose the nose as the feature that you noticed first or that your brain locked in on first as your visual cue. You might think that this is an image of someone facing directly towards the camera, and then it's just got this funny cutoff of the face going through the whole picture. But others, say you focused on the hair or on the eye of the person in this image, you might view the person as facing to the left of the screen, almost towards my mouse, which is sitting on the left side of the screen, right? So our brain is constantly picking pieces of information, especially when images like this one don't make a lot of sense. Faces are something that people are really, really used to looking at. So it's really easy for us to pick out features and traits that we're familiar with, especially in an image like this one that might look pretty funny. All right, now I've got two more illusions to show you. One of them is here inside my studio on my studio camera. And this one is an illusion that has to do with the refractive index of water. Now we're going to take some objects and put them down inside our vats of liquid here. And we'll take a look at what happens to the objects inside. Now, this is something that you might have noticed on your own. Even before you knew this was an optical illusion, you might have noticed this happening just with objects that you drop down inside clear liquids. So this big beaker is full of water. And what I'm going to do is just take a pencil and set it right down inside the glass. And we'll just take a look at what the pencil looks like. Now, this illusion is normally called the broken pencil because the pencil almost appears like it's broken because of where the pencil meets the water and then how we continue seeing that image once it gets down inside the water. Now, there's some magnification happening. So one thing we notice is that where the water covers the pencil, that the pencil might look a bit wider. But the most important thing we notice is that where the pencil meets the water, it almost appears to split and then start back up at a different point, just like my fingers are doing over here. This has to do with the refractive index of water. So we've talked about frequencies of light a few times here on Echo Live, and we've talked about how light travels through the air at a constant speed. But when it travels through something, the speed of light changes. And light actually travels much more slowly inside water than it does through the air. So when that light that's traveling to our eyes has to travel first through the water, the light will actually bend. So in the case of this pencil, while it's originally traveling in this direction, once it reaches the water, it will actually shift downward, down towards the tabletop instead of continuing along that linear path that our brain might expect. So we can do this with other objects as well. So I also have a glass stir rod here, and that broken pencil effect might seem even more noticeable. This is partly because now we have two different refractive indexes coming into play. We have the light traveling through the air, then through the water, which bends the light of the and then it also has to travel through the glass, which has a different refractive index. So this appears to be even more broken than our pencil did because now there's an even bigger difference between the speed of light traveling through the air around the beaker and through the glass and through the water inside the beaker. So this is a really, really simple one that you can try at home. But I also have a different liquid over here. Now, this only works with clear liquids because we're talking about refractive indexes. And refractive indexes really only come into play when you're talking about substances that allow light to pass through them. So it has to be clear or at least partially clear in some way. So this is mineral oil. So mineral oil is here inside our second smaller beaker, and it has an even different refractive index than water. So let's go ahead and we'll first try the pencil. And you'll notice we still get that broken pencil effect where those two lines meet. The pencil almost appears to be broken as those wavelengths of light slow down as they pass through our mineral oil. So we can tell that the light travels more slowly or more quickly, depending on what the substance is. And we actually see that bend or that break in the pencil. And you can see this is mineral oil. It's really, really kind of sticky, thick stuff. But let's watch something even cooler. So let's take our glass stirring rod out of our water and drop it down inside our mineral oil. Now, is anything funny happening to that glass stirring rod? Does it look any different than how it did in the water? And I'll grab another one. So tell me, what do you notice? Is there anything kind of strange happening? Tell me what you notice or what do you observe, right? Because we're all just relying on the visual cues that we get from our brain or from our eyes to our brain. Here we go. So I've got another clear one so we can kind of see the difference. Now, is there a difference between these two stirring rods? Yeah, people are telling me yes, right? The stirring rod in the mineral oil almost appears to be invisible. It almost looks cracked. And I think that might be partially because there was a little bit of water left over on our glass stirring rod. So let's completely dry it off. Make sure that we have no other variables to think about other than just the refractive index of the glass and of the mineral oil. And while we can see the glass stirring rod pretty well here inside our beaker full of water, the glass stirring rod inside our mineral oil almost appears to disappear completely. This is because the refractive index, or the speed that light travels through mineral oil, is almost identical to the speed it travels through glass. So we actually observe that as we can't observe it. Our eyes actually can't process this because the light is traveling through both those objects at the same speed. There's no difference for our eyes to observe. And so it almost appears to disappear in this substance, even though we know it's there. So that's an optical illusion that you could try at home. All right, I've got a couple more with the last few minutes here on Echo Live. This one is one of my favorites. It's called the trizonal space warp, and it involves you trying something at home with me. So I'm going to pull up a video here of the trizonal space warp, and we're going to play an image, and there's some instructions here on the screen. This trizonal space warper was invented by a guy named Jerry. And so Jerry, since he named this something kind of cool, he wanted credit for it, but you'll get a closer look at Jerry later in this video. All we need to do is once the image starts playing, the image will play for 30 seconds. You just want to stare at this trizonal space warper for as long as you can. Try not to blink. It's only 30 seconds. If you do blink, the illusion will still work, but just stare at this image for the full 30 seconds and then watch carefully what happens to Jerry, whose picture you'll see at the end of this video here. So let's take a look. All right, so you should be trying not to blink, staring just straight at this image, maybe even right at the center of the dot in the very middle of our trizonal space warper. So right now, our brain is receiving all sorts of cues from this image. We can see that these lines are moving, they're changing shape as they appear to get closer or farther away from the image. And then look what happens to Jerry. Now tell me in the chat or the comments feature, what's happening to Jerry? What do you see or what do you notice? This one is one of my favorites because it's a really cool optical trick. I noticed, Becky tells me that he's old, and unfortunately that's not an optical illusion. Jerry is a little bit of an older guy. If it didn't work, we'll post a link to this video so that we can try it again. We can try it one more time all together. Tell me in the comments, was the trizonal space warper, did you see it moving when that video was playing? Oh, I'm seeing some answers. Some people are telling me that his face moves or warps a little bit. So we can maybe see why this video is called the trizonal space warper. Let's try this one more time. So we'll start our video over here and get my keyboard out so we can share that video one last time. All right, let's share the trizonal space warper. And remember, the object is to stare at this image, kind of let your eyes relax, but just stare at this image for the next 30 seconds. And then watch what happens to our picture of Jerry. All right, so right now, our brain is getting cues about movement. So the parts of our brain, that's spatial pathway or dorsal pathway, is telling us about something moving. But our brain takes time to adjust to changes in sensory cues. And since that last image was moving so much, when we start to stare at Jerry, our brain has a hard time distinguishing that that image was actually not moving. Jerry's image was completely static, but if you try that enough times, you'll notice that Jerry's face almost seems to warp and wiggle and shift back and forth because your brain is still seeming to receive cues about something being in motion. So our brain is an incredibly powerful tool. So far, we have not been able to have computers or artificial intelligence actually create an optical illusion of their own. So AI or artificial intelligence and computers can do all sorts of things that humans can do as well. They can write songs that people really enjoy just based on formulas and calculations about what makes people enjoy certain types of music. They can write stories. They can speak in a way that sounds like a real human. But since this pathway is so unique to the human brain, computers are not actually able to recreate it. It's something that scientists are actually working on because they think that's an interesting problem for computers to try to solve. So remember that when an optical illusion is tricking your brain, that's because your brain is one of the most powerful computers or tools on the entire planet, and not even the most powerful supercomputer can recreate that. So I have one last image to share with you before we head out for the day. And it is, of course, one of the most famous optical illusions of the modern age, which is the dress. Now, the dress came out on social media a few years ago, and the internet was divided over, is the dress blue and black, or is the dress white and gold? So if you have not voted, or you've seen this image before and you have an opinion, tell me in the chat, is this image, or is the dress in this image, is it blue and black, or is it white and gold? Tell me what you think in the chat. So let's take a poll at first, and then we'll talk a little bit about what's happening in this illusion. Ooh, a couple friends on Zoom are telling me white and gold. I definitely see blue and black. I have not really been able to get my brain to think that this image is white and gold just yet. Sometimes I get almost there, just like with our spinning dancer, and then my brain goes right back to my original thought, which tells me that it's blue and black, not white and gold. Maureen tells me it's blue and gold, so she might see something even different. So now that we've got a few guesses coming in, let's talk about why this illusion works, or what's happening in this version of an optical illusion. Our brain, like we said, relies on context. It's not just thinking about the object in front of us. That would be all part of that object pathway, the ventral pathway, but it's also taking information about what is around the object. It's comparing the object to its environment to learn things about size or shape or distance. And for this reason, depending on the context of the photo, depending on which pieces of the background your brain is picking up, you either view this dress as blue and black or as white and gold. Or Maureen is actually telling me she sees blue and gold, which is really interesting that our brains can all see the same image so differently. So I have almost a good explanation, or a good way to try to explain this to you. So we have shapes A and shapes B. They are the same shape, just kind of mirror images of each other. And A appears to be much darker than B. So the block on top appears to be this dark gray color, whereas the block on bottom appears to be kind of a shadowed white color. But both of these blocks are the exact same color when you look at the surfaces where those letters are labeled. The best way to try to force your brain to see this is that you close one of your eyes and hold your finger up over the barrier between them. So if you kind of cover this line right here, let me see if I can draw on this to see. So if I draw on this, so if we cover up the center of this image, now our brains can see that these two blocks are in fact the exact same color. Without the block, our brain is comparing them to these shadows. Our brain is taking context clues from the environment, which forces us to think that A is darker than B because of the context it's sitting in. But again, if we cover up that barrier, if we remove the context clues, we're left with just the two images, which are exactly the same color, which is pretty fascinating. And that's the same science, like we said, behind the dress. So depending on which part of the background your brain is comparing the dress to, you view the dress as different colors. Now, if you have any questions about the experiments that we've done here on Echo Live today, or about the optical illusions that we've shown, go ahead and type them in the comments or the chat feature. I'd love to answer a few of them before we head out today. We are just about out of time, so big thank you, as always, to our generous sponsors of the Michigan Science Center, like Ford and Denso, who are allowing us to bring our Echo Live programs to you every weekday at 2:30 p.m. Eastern. These programs are free. We want you to participate every single day if you are enjoying them. As always, make sure that you are liking and following the Michigan Science Center's Facebook page so that you get an alert when we go live every day. And you are always welcome to share these videos with your Facebook audience as well, so that they can join into these programs as well. All right, so if you do have questions, let me take a quick look through our chat. No questions coming in just yet, but I'll take that as a sign that we learned a lot and we're really excited to head home and try some of these illusions at home today. If you're looking for at-home science to try, as always, visit the Michigan Science Center's website. Check out some of our try this at home science experiments. We've got lots of them on there for you to try. And if you do try them at home, say you create one of your own optical illusions today or this weekend, tag the Michigan Science Center so that we can see the results. Thank you everyone so much for joining us for another episode of Echo Live. We'll see you back here tomorrow at 2:30.